Let's see. All right. Now I think we've got some streaming going. We're earlier today, or at least the live stream is earlier today and tomorrow. Tomorrow it'll be the same time. I think next week it'll actually be a little later than normal, like 9:30 or so. But we'll deal with next week once we get to next week. We've got two other things this week, today and tomorrow. Today, what I thought we would do is we'd look some more at slicer settings, but in the context of you want to print stronger parts. So one of the things you might want to do is you might want to print some of these parts and actually use them for maybe a prototype or actual part. And there are some things you can do in the slicer to create stronger parts. And so we're going to talk through how that'll work. Along with one other thing is one of the common upgrades, like one of the not very expensive, maybe $20 range or cheaper upgrades that you might think about doing. And there's a couple of different types of that particular thing that we'll look at. And just so you'll have some ideas of what you're going to have to do if you want to do that upgrade. Let's look first at kind of our schedule here. So I have not, I'll probably grade stuff that you turn in once a week. So Friday or around Friday, Saturday, somewhere in there, I'll go through all the turn-in things and see what has been turned in. Remember, these dates here are just like suggestions. They're not hard due dates, other than the end of the quarter is obviously a hard due date. But based on what I think, if you're keeping up with everything and you're not getting behind, then by the end of this week, you should have gone through the calibration prints. So we actually looked at one of them, the temperature tower. We actually looked at it last time, but there are a couple others that are in that little part of it. Well, here they are right here. There's a retraction test. We haven't really talked about that one. Temperature tower, we talked through that one. Tolerance test, we haven't really talked about that one either. So I linked some Thingiverse files here that you could use, or you can use the versions of these that are in the Cura plugin. They'll be a little bit different. They're all trying to do the same types of things though, so it doesn't matter if you pick one that's a little bit different from the ones that I have linked here. These are just ones that you could do. But by the end of this week, if you've gotten these 3 prints done, now I will say you don't have to repeat these. So the retraction test is actually a pretty quick test, and so you might print a couple of those, but you don't have to try and get these perfect. The idea is that you just know they exist and you print at least one of them. And then if you want to improve it, then that's on you to do. But as far as the course credit goes, you just need to show that you printed one and you have an idea of how to read it. So you print one of these retraction tests and you take some pictures of it and you read it. So you look at it and say, oh, it looks like I need to increase retraction. It looks like my retraction is fine. And so we'll talk through these. Actually, we probably should talk through these now if I'm telling you that these need to be due on Friday. Oh, they don't need to be due on Friday. That's my idea of, if you've gotten them done by Friday, then you're probably on pace. We already did the temperature tower. The idea there is that each roll of filament could have a ideal temperature to print at. Remember, we did ours. It's kind of over here, this guy, and it looked pretty much the same at all temperatures, which made me think that it may not be that my printer is being limited by printing at a certain temperature, but maybe it just isn't cooling well enough, because they're not perfect. They're pretty good, but they're not perfect, and they're all about the same. So I could probably deal with some new better cooling. I'm going to show you. Let me take a little detour. I guess I take lots of detours, and show you what I'm going to print to maybe, hopefully, improve my cooling. I usually go to Thingiverse. Thingiverse is a website that has a lot of free STL files that you can download and slice and print. But sometimes, like today, apparently, it can be really slow website or difficult to navigate. Right now, it doesn't look like it's going to give me anything. So let's take an alternate route here, and let's look up Ender 3 fan duct STL. STL is stereolithography. Well, that is one thing. It is stereo. In this case, it is. I can't remember the definition for STL right now. In this case, it is a file format that is nothing but taking your geometry, your 3D geometry, and turning it into a bunch of triangles. Let's see if we can find one that looks like what I'm... There are lots of fan ducts. I'm looking for one kind of like this second one here. Oh, this one looks kind of nice too. I want one that's going to just snap onto the existing fan, bolt in place so I don't have to change anything other than the fan duct. But it redirects the air from that fan, the one on the side, and it redirects it kind of on both sides of the nozzles. That's what I'm looking at. And this one seems to do that. That's not the one that I normally use. Some of these are requiring new fans, additional fans, you know, all that kind of stuff. This kind is one that you can do. It kind of creates a whole ring of air around the nozzle to cool the part. Thingiverse still hasn't loaded up. That's good, but it's still a little more complicated than what I'm looking for. I'm kind of looking for one that is a little simpler geometry, and I don't see it currently. But that's what I'm going to print. I'm going to print just a little snap-on. Actually, it does screw in into the fan, but you just use the existing screws. And I don't see the one that I normally print. I'll have to dig for it a little bit. It is similar to this very first one, but it's not quite like that. Although this looks like it might be a good one to print. Let's see if we can grab that one. Sometimes some of these other My Mini Factory will have paid or free parts. It looks like this one's just free, so it just says download with no pay or anything. Sometimes you can support them, like you can send them $1 or whatever. This one looks reasonable, but it looks like it's got a little more complicated geometry than I want to deal with on printing, but it does look doable. I might try it. But that's what my goal is. That's what my first attempt at improving the cooling of my printer is going to be. Let's see where we at. We finally got Thingiverse to come up. Let's see if we can find the one that I normally get. It might take a while for that to come up. Oh, this is it right here. This is the one I normally print. So it's just going to snap into the existing fan. You have to take off the existing fan duct. And then these little holes here will screw into the fan mount screws that are already there. So it's really easy to do. And it doesn't go all the way around the nozzle, but it redirects, halfway around the nozzle, redirects the cooling air halfway around the nozzle. You would think it's going to be right up against the nozzle and melt, but it's far enough away. And most of these nozzles have the little silicone sock on them that kind of insulate them from radiating heat. And I've never had one melt. So even out of PLA. So you can print these with PLA, put them in place, and in my opinion, they work better than what's on there already, on the Ender 3 anyway. Better Ender 3s, like the Pros and all that, those might have better cooling ducts as part of them. The baseline Ender 3, it does cool, but it doesn't do a whole lot. You can even see when we did the prints with no cooling at all, they weren't that different from the ones that had cooling. So I'm gonna print this guy, probably not today, but I'll print this one as my replacement fan duct, and we'll do that. Back to where did we go with our, that's something for later. So that's what with the temperature tower. Again, you just print one of them. You don't have to print a whole bunch of these, and you read it. So you say, looks like my printer doesn't have, with this filament that I've tested, because a different roll of filament could be a little different. It looks like safe printing temperatures are between this and this, whatever. Or it really prints best at 205 or whatever, and that's all that you need for that assignment. Retraction test, let's see if I click on this, if it actually gets there in reasonable amount of time. Doesn't look like it's going to. Why don't we just go to Cura's retraction test. Let me get over to Cura. There it is. So Cura's Retraction Test, the built-in parts for calibration, they have all of these. They have a retraction tower, they have the temperature towers that we already did, and they have a, I thought they had a this calibration, I think it might be the dimensional accuracy test. We'll have to look at that. But let's look at their retraction tower. So, got this guy, and that looks more like a, yeah, I guess that will work for a retraction tower. It's not really the one I was thinking of. Let's see if they have a different one. All right, let's do the Retract Test. That's more like what I was thinking of. All right, so just two, I mean, this is a really fast print, but it's just two little columns. One happens to be tapered so that you're using a little bit smaller movements on one end gradually, because it's a cone. And the idea is that the print head has to print on one side, and then it moves to the other side and prints, and then it goes up a layer, prints, moves, prints, and you're looking for this zone in the middle. What the retraction is going to do is it's going to really retract the filament that's in the tube. So let's look at, oh, our camera went off. Let's look at our, I lost my camera. There it goes. I'm not sure what happened there. But let's look at our tubes here that I'm talking about. So back behind here, you can kind of see the edge of it, is where the filament gets fed into the whole system. And that white tube here, filament runs through the center of that, and then it comes out of your nozzle. Well, this is a Bowden tube, and what this is called is a Bowden tube setup compared to a direct drive setup. So it could be that you've got an extruder or I'm going to call it a feeder, so it feeds the filament into the hot end. So you've got that motor sitting basically right on top of where the filament is being fed into the hot end, and then it comes out, it gets melted and comes out. That would be direct drive. We'll show that. I have a printer over here that's direct drive. When we'll look at that, I don't know, in a couple of days. But the downside of that is you've got this big heavy extruder sitting on top of the part that has to move, so it kind of weighs down that axis. So it might slow down your printing speed a little bit. Typically on this style printer it doesn't matter because you're limited by having to move the bed, which is even heavier, so your printing speeds are going to be limited by that anyway, so it's fine. But some printers the bed doesn't move, or at least doesn't move back and forth. Some printers the bed doesn't move at all. Other printers the bed drops down, one layer height at a time, which is not going to cause a lot of ringing or ghosting or skipping steps, layer shifts. It's just not going to do it. These, where you have to move the bed back and forth, we call those bed slingers because they're slinging the bed back and forth. They're usually limited in their print speed by how fast you can accelerate and decelerate and then change direction of the bed itself. So it doesn't matter if you put a big stepper motor on top of here, it's still not going to be as heavy as the bed. Anyway, so this tube here, the filament inside there basically ends up being a really long spring. And so if I stop feeding filament over here, the spring, like it's a spring that's been compressed, it's gonna have want to release that compression in the spring, the filament. And if I can stop here, but there's still going to be filament coming out because it's basically releasing the compressive stress. Well, yeah, it's probably a compressive stress that's built into the filament when you try to push it through the hot end, and you're going to get a bunch of oozing, and that's going to show up in a print like this, where I just finished this layer, and then the nozzle has to move over here. While it's moving, then that filament is going to ooze out, and you're going to get strings between the two columns here. Typically, you don't want that. Now, they're usually pretty easy to clean up. If they're little wispy, real thin things, you can just blow hot air on them like a hairdryer type thing or a heat gun, and they'll disappear. If they're thicker ones, then you can usually, cut them off. Where's my screen? Cut them off with some of these things. and that's fine. But maybe you just don't want to deal with that. You just rather them not be there, which is ideal. And that's where retraction comes in. So retraction is a setting. It's usually not one of your basic settings, but if we search for retraction, then you'll get enable retraction, and you've got a lot of settings here that are related to retraction. What retraction is doing is whenever you stop printing, but you're still moving, so you're moving from one spot you're going to print to another spot, this filament will be retracted. It'll be sucked up into the tube so that it doesn't ooze out the bottom. And you've got settings. Whoops, wrong thing there. You've got settings. Basically, the most important ones, actually, probably the most important one is the retraction distance. That's also the one at the top here. But you've got a lot of others too. And what this is how many millimeters are you going to suck the filament back into the tube. And so the default, I haven't changed these, this is the default in Cura for Ender 3, is 5 millimeters. And retraction speed is also like a second most important thing that you would do. So how fast are you going to do that? And 45 millimeters per second is the default. And then you've got a lot of other deals over here that you can mess with. I would, until you like go and read and figure out what each one of these little things does for your retraction, I would just really probably just do retraction distance as the thing I change. Maybe you change retraction speed, but I would probably focus on distance. So the idea is you print one of these things. Again, for the course assignment, you just need to print one and then read it. So you write up a little thing. It looks like my retraction I could use more retraction. It looks like I have limited stringing, and so it is fine, or whatever your print looks like. These are really short prints, so you might actually do more than one of these. But you do one. Obviously, the larger amount you retract into the tube, you'll have less stringing, but then you've got to spit all that filament back out to get started on the next layer. So too much retraction will cause holes in the part that you moved between. You printed on one side, move to a new part, and start printing this other one. If you don't get the filament back in time, unretract it so it's ready to print, then you'll get holes in the new section of your part that you retracted to get to. So there's an ideal amount of distance here. But if you're having lots of stringing in your parts and you want to kind of reduce it, this is a way to go about doing it. Now these tiny little columns here are going to be kind of worst case scenarios where you print and then move a little bit and print and move a little bit and print. A lot of things that you actually print don't have that geometry, so this is going to be a worst case one. Don't be surprised if you can't eliminate stringing from this little tiny 2 columns next to each other. But that's the retraction test. And then the other one is a tolerance test. Let's again see if Thingiverse is going to open this thing up. No, doesn't look like it's going to. Well, no, here it goes. I like this. This is a longer print, and I would really only do it one time. But what this does, it prints this. There are 1, 2, 3, 4, 5, 6, 7 little cylinders that are, let's see if we can get this to load up where I can move it around. There are labeled with different numbers here. These numbers are the gaps between the cylinder and the housing. And so 0.4 is the 0.4 millimeter gap. And then it goes down, this particular one goes down to 0.1 millimeter gap, which I don't know how to, oh, there we go. So you can notice that there's a really tiny gap between these, much bigger gap here, and then it goes by 0.05 millimeters from 0.1 down to up to 0.4. The idea here is that on the other side of this print, there's these little, whoops, clicked on something. There's these little hex, like you could get a Allen wrench or a hex key and try to turn these. So the idea would be that you can figure out what is your printer's resolution, basically. And I would think that a good setup you'd be able to break the 0.2 apart without too much trouble. below that, the 0.15 and the 0.1, those might be actually fused together. So you could work on, trying to get that perfect, but this is kind of a flow rate calibration. You're spitting out the right amount of filament for what the part is asking you to do. But it can get really tight if you're trying to manage a 0.1 millimeter gap, where both sides have to be extruded perfectly or else it's going to fuse together. So again, hopefully you can at least get the 0.4, the 0.35, the 0.3, and probably the 0.25 to break away with just your hands. Maybe you need a little bit of a Allen wrench to open them up. 0.2, Allen wrench should break that apart. Below that, not necessarily, but if none of them open up, that's fine as far as the course goes. You just describe that it looks like my printer is really over extruding and fusing everything together. Why this is important is there are a lot of parts that you might want to print that are called print in place, and they're articulated, so they have moving parts, but you print them all together, and then the idea is that they will have a sufficient gap between the little connecting pieces that they'll articulate and move around. Or also you want two parts that are printed separately, but you want them to interface with one another. If they're off in dimension, like they're over extruded so the walls are thicker than they should be or whatever, then they won't fit together correctly. So what this will do is it'll tell you about your printer's flow rates and ability to hold these gaps, so that if you're designing a part, you know kind of what kind of gap size tolerance to design into the part you're going to print. So I'm not sure if Cura has a built-in one of these. Let's see. Well, I thought I saw dimensional accuracy test. No, that's more like you're measuring it. That doesn't have an articulated part. That's not really the same thing. I don't know that they have one. Let's see what this one is. Yeah, more of the same kind of you measure that you're printing correctly. This one you don't have to measure anything. You just do the cylinders turn or not. So I don't know if they have one that is going to do that built in. You might have to go download it. I like this one because let's see if I can get back to the, there we go, this cross section. So what you notice down here is these little chamfers on the bottom. The bottom print of the bottom side of a part a lot of times is squished because you've really squished down that first layer, and it expands, and that's a different thing that we can try to deal with other ways. But this part gets around that by chamfering it, so if it squishes out, it's still not going to fuse together. So I like this one. It does a good job. It is a longer print though, maybe an hour and a half or more to print it. Maybe 2 hours. I don't remember. I guess it depends on how what layer thickness you're going to use. All right, so those are the 3 calibration prints that if you've done one version of those by the end of this week and uploaded it, you're pretty much on pace. If you haven't, you're still fine. That's about where you should be. All right, so we've talked through some slicer settings just in the retraction. We didn't really talk about flow. We'll do that a little bit later. I'm going to take these slicer settings and talk about in the context of I want stronger parts. So there are a couple of things you can do in Cura to get stronger parts. First, let's get out of there. All right. So one thing you can do is you can just create more walls. So one wall is pretty thin. That's not going to be a very strong part. If I'm trying to print something that I want to actually function as a part and not just, a decoration, then I'm usually going to do 4 walls on that part. Now it does increase printing time a lot because walls are printed slower than infill. Infill is usually about twice as fast as a wall is, or more. And so it is going to slow down the print time, but a lot of strength is gained from just having the walls themselves. I will usually put, let's see, top and bottom layers, I will usually do those at 4. So I've got kind of 4 perimeters all the way around the part. Infield density, I usually don't go above 25% to make it it's not solid. One thing you can do is print a completely solid part. That is usually not going to give you that much more strength. It is stronger, it's solid. It's going to take a significantly longer time to print, but you could make a 100% solid part and use that. I don't think that's usually the best way to go, unless you just need this thing to be a solid piece of plastic, which there are cases where that's what you need. Most of the time, if you're just trying to fit something together, or you want to use it, but it's not like a production part or anything like that, then these settings will be good. You don't need to make a solid part. I usually do the gyroid infill pattern. To me, it gives a little bit better uniformly distributed density inside. Some of these infill patterns are very strong in one direction and not as strong in other directions, but the gyroid is pretty uniformly strong. So I usually do that one, and it's not terribly slow either. It's a decently fast pattern. You might print a little bit hotter. Remember last time, or one of the earlier times, I said that there was a student in the last, actually it was a separate project, it was just a project they did, who went through and, let's see, I actually have the, that's what was pulled up. Where did I put it? There it is. So they went to ASTM standards, got the dog bone shape. So this is only in tensile test. It's not a bending test or anything like that, but tensile test. So this was one of, I think they did 25 samples at 5 different temperatures each. So 5 samples at each temperature. And this is what the data looked like. So you could see, there's some variation, obviously, because it's still printed parts and they're not going to all be same from one to the other. But in general, there's an increase. This y-axis is maximum force in newtons that was applied to the tensile test specimen to break it. And there's a trend upwards that as you get increasing temperature, you get stronger parts. Now, is it true in every case? Maybe not, but in this tensile setup, it does show a more or less, linear, probably need some more samples to see if it's really linear, rise as temperature increases. He did from 195 to 210. So a lot of times you'll get a roll of filament, and yeah, let's see, right here off on the side, it gives you some range. One for this particular roll, 190 to 220. That's a pretty big white range to print in, but you'll get something like that. So took that range for whatever filament he was using, and went from 195 to 210 and divided it into 5 intervals, and kind of showed that yes, it does increase. Now, does it continually increase if you go to 215? It's probably not. At some point it's going to get too hot and not print very well at all. But in this range of ideal printing temperatures, there is a stronger part, at least in tension, as you increase printing temperature. And that makes sense because the layers are being better bonded together. A lot of times printing hotter, you lose a little bit of your surface finish neatness. It might be a little bit lumpier or whatever, but you gain strength and in general. So that's one way. That's another way. You could just, let's go back to Cura. You could just print a little bit hotter. Instead of your 205 you normally print at, you go up to 215. And so that'll give you a little bit better bonding between the layers. You can slow down your print speed a little bit just to get that better seating of one layer on top of the other layer. I don't know that I haven't done an experiment that printing speed changes strength or not, but that is another thing you could do, is print a little bit slower. I don't know that I would say that 100% guarantees a stronger part though. Let's see. You could, if your print would handle it. Some prints, you know, the geometry is not going to do well without cooling, but you could turn off part cooling, or well, it's called print cooling here, and that will also, you know, keep the layers hotter longer. It does with PLA kind of destroy the surface finish of your part, particularly if there's any kind of bridging that has to happen, like the bridging that you would have right here. So if you have a part like that in PLA and you want it to be able to bridge, you probably can't turn off the part cooling like this. But that would also, assuming that you could print it successfully, then turning off part cooling would also make it a little stronger. I'm not sure, I haven't done the experiment to see exactly how much stronger, but stronger. So those are things just in changing settings. You don't have to do anything else, just changing settings that can create a little bit stronger part. Let's look at one other thing before we move on. I'm going to create a little thing. So this is Tinkercad. Oh, well, let's look at it in a better view. There's Tinkercad. This is a Autodesk, so same people that make Fusion 360, or well, I don't know who made all those things, but they own them now. So Fusion 360 and what's another? AutoCAD. That company. They have this thing called Tinkercad. It's a browser based, so you don't have to download anything. It just works in your browser. It's free. You'd have to have an account, so you have to log in and sign up for an account that is free. But if I'm going to make it just a really quick part and I don't want to wait for SolidWorks to load up or Fusion 360 to load up or anything, I don't want to deal with all of that. I just need a simple little thing. I usually go to Tinkercad. It is a different type of modeling from Fusion 360 and SolidWorks. It is more of I take a bunch of blocks and mash them together and subtract them, Boolean type stuff, where Tinkercad, where SolidWorks and Fusion 360 are more, I draw a profile and extrude it or revolve it or whatever. So it's limited on what you can do, particularly if you already know how to run SolidWorks or Fusion 360. But if you just want a really quick part, it's probably what I'm going to do. So just create new design here. I'm going to create a part. I'm not going to, this isn't a Tinkercad tutorial. I actually have one that I've done in the past. So I'll link that one. It's like 20 minutes long just to show you the ideas of Tinkercad. But let's say that we need a little plate that's got some holes in it. Let's say there's a hole there and one over there. Okay. So got to make this little bracket and it's got some holes in it. Let's actually make the holes in there. Right there they are. And I'm going to export this as a STL. Now it always gives them these weird names. You can change these names, but make sure that if you don't change the name, you know what it's calling it here, so that you can find it later, because the names are, you know, like some kind of adjective and a weird word. But you can rename them. So Fabulous Memu is what mine ended up being. So let's import our Fabulous Memu. There it is. So there's my little part. Oh, notice these are very faceted here. Oh, hold up. There we go. These are very faceted. They don't have to be. It's not like a limitation of Tinkercad. That's just the way I made the part. I could have made them more smooth. So don't think that Tinkercad can't make smooth circles. It can. I just didn't bother to do that. All right, so there's my part. And I can do all these things that I've already done. Let's slice it and preview it. And so, you know, right away you can see the 4 layers, 4 lines. It does put the 4 lines around the hole. Let's say that, and it's going to take, let's see how long it's going to take. 1 hour and 9 minutes. So that's not horrible. I could deal with that. Let's look at that gyroid infill pattern. There's the gyroid infill pattern that I usually use for a part that I want to be stronger. So you can kind of see how it works. Let's say that that's okay, but I want to make it faster, and I don't really need the strength on this outside, but I need the strength around the holes. So I'd like for the holes to keep 4, maybe even 6 perimeters, but the walls, they could really get away with 2 perimeters. So there is a way, and I might have to stumble through this, but let's do our wall line count at 2 and slice it. And now I've got 2 walls, which also did the 2 perimeters around the holes, which is not strong enough for what I'm thinking I need. But it's good enough for the rest of the part. It actually didn't seem to reduce my print time by anything but 2 minutes, which that's telling me that my infill is taking up most of the time for printing. So I could change to a faster infill pattern if I wanted to, or a less dense one. But let's say that I just want to increase the number of walls around here. One thing I could do, which according to the estimate is just print everything with 4 walls, and that's fine. Sometimes that doesn't work out, and it really is taking a lot of time to print the perimeters. I can selectively, and you could do this with other things too. It doesn't have to be just walls. It could be any one of the features that I want to deal with. Over here on the left-hand side, I have these per model settings, and I can go in and let's see. I gotta remember how to do it here. I need to. Oh, I think I just add a box. Maybe. Hold up. I might have to. Oh, get off of there. Oh, I'm in the preview mode. Let's go to prepare mode. There we go. I don't want that to actually there. I think I need to add. So let's add cylinder here, and let's have this cylinder move to where it overlaps. So this is a bigger cylinder, right? And I'm kind of surrounding the hole that I did have. And let's copy it and make another one. Multiply. And let's put it, I'm not being particularly like sophisticated with where I'm putting these right now. But I've got these 2 guys selected. So just held down shift and selected both of them. And then I've got I guess I have to only do one at a time. Per model settings, the overlap, I want to change the wall count to wherever this part overlaps my plate to have 6 walls. Okay, and then same thing over here, wherever this one overlaps the plate, or anything, it doesn't have to be the plate, just anything it overlaps, I want to have 6 walls. So I have control over wall thickness, wall line, top and bottom number of layers, and I have infill mesh only, cutting mesh. I think we'll leave it at infill mesh only. I thought I had a, I guess infill percentage is not one of the ones it puts out here, so you have to go to select settings and select infill. But now when I slice it, it should give me more walls around those parts. Oh, but it did it in the infill. That was the infill part. Probably I needed to do the cutting mesh because that looks a little weird how it did that. Let's go back to here and let's select this thing and let's make it cutting mesh. And let's do wall line count at 4. Or I did 6, didn't I? And then let's change this one to cutting mesh so that everywhere it overlaps instead of just overlapping the infill. Wall line count. Keep forgetting to close that. It's 6. So you can, selectively apply certain settings to pieces of your model where they overlap with these cutting meshes. So there it is. Still acting a little bit weird on here, like with this little moon shape, where it's. I'll have to dig into why it's doing that particular thing. Oh, it's doing the walls for the part instead of making it a solid part. It's just only where it overlapped. That's what it's doing, and it's using basically just the perimeter of this thing. Maybe I should make it normal model, but then it's no. I need to overlap. I'll have to see why it's doing that particular way, but you can, if I size this better, like to make this cylinder the same size as my hole, or the size bigger that I wanted it to be, printing those walls, then it would work a little bit better. I roughly put this together, but you can use these, I don't even know what they call them, but overlapping models. You can use these overlapping models to selectively change print settings for just a region of your part. And that's another way that you can get strong parts where they're strong where they need to be, but maybe the rest of the part is, just kind of your regular 2 walls and 15% infill, stuff like that, so that you can save some time printing the part, but still have it strong, or whatever you need. It doesn't have to be that you're making it stronger in one part. Maybe you just need more. You need one part to be less dense or hollow or something like that. And so you can change out different pieces of your model to have different printing properties. So that's a way to do that. All right. So those are some slicer settings that you can go in. Layer height. I don't think I've ever actually tested this like we did with the temperature, increasing temperature to make increased strength. But you would think that if you increase layer height, that would make a stronger part, just on the sense like whenever you do a size factor for a part that maybe is in fatigue, and you have these strength reducers that go in and say, well, the bigger the part is, the more likely it's going to have a defect in it. So the same thing could be true. I haven't actually done an experiment to test this, but the same thing should be true, that the more layer interfaces I have, the more likely that something's going to go wrong. So thicker layers, like 0.28 versus 0.2 or 0.15, should have fewer interfaces, and statistically you should end up with a better part, just on the sense that you have fewer chances for bad adhesion between the two layers. I haven't tested that to see if it actually plays out that way, but I could make an argument anyway that increasing the layer height would also increase strength, because you have fewer interfaces between your layers. There's just fewer layers total. That would be, if somebody wants to do that as a one of the little technical memos, that would be an interesting thing, is does layer height affect different types of strength, so tensile strength or flexural strength or something like that. I think it would make the most sense for a flexural, like a 3-point bend test. Anyway, so obviously increasing the wall line count, what I normally do is 4 for a strong part. Increasing top and bottom layers to about 4 usually creates a stronger part. Printing infill a little bit higher than what I normally print. I think 25 might be kind of the default in Cura, but if you go up beyond like 70%, then it's pretty much solid at that point anyway. So if I really wanted this to be a solid part, I wouldn't actually change the infill. I would change the number of top layers to something like 1,000, and then slice it. Everything becomes a top layer, and so it's a solid part at that point. I don't know what it's going to do with my little block yet, but everything's a top layer, right? So it's a solid part. That's how I would create a solid part if I were going to try and create a solid part. It changed our print time. It was to not that much more. That gyroid pattern is pretty dense. So right here, the gyroid infill pattern is pretty dense. So it's already going to be a relatively solid part, even when it's only 25%. Increase your print temperature a little bit. Maybe decrease your print speed. I may or may not do that. Usually I don't do that. And if it's possible, you could turn off the layer cooling. So that would just keep the layers hotter for longer so that they bond together better. So that could create a stronger part. All right, for the last few minutes, let's look over here. I talked about a upgrade that you might be interested in, and it's right here. So on your Ender 3, this is the part that I'm going to have to move some stuff around. Let's get this guy. We'll have to zoom out, and let's look over there. All right. So this one, this red piece, it's already been kind of wobbly. Already been replaced on this one. The starter piece for here is usually plastic, which is fine except for two things. One thing is this little hole right there where the filament comes in. If it doesn't have a metal insert, then this filament is eventually going to wear a groove in that plastic part. Like at some point, it'll wear all the way through the thing, particularly if you have your filament coming from up higher so that it's kind of abrading that hole on the top side. It'll eat through it. Most of the printers now, I think, that have plastic handles right here have a little metal insert that eliminates that problem. The other problem, though, is that you'll get a crack on the bottom side of this piece, this little lever. This little lever is holding, let's see, it's holding this roller against the drive wheel over here with this spring. And it will eventually crack if it's plastic. And it usually cracks on the bottom, so you don't see it, because the bottom has some other features in there. It has this hole, you know, and the hole's on the top also, but it usually cracks on the bottom. You don't see it, and it looks like it's still working fine because it doesn't like snap in two most of the time. It just cracks. And what that does is it doesn't allow this spring to apply all the force it needs to on this filament, and the filament will slip. So your prints will be kind of very unpredictable. Sometimes they'll work fine. Other times it'll look very under extruded, so kind of hollow looking. And so a lot of times you want to upgrade to a metal one. And there's two types of, or there's a bunch of things, but two main things that end up the things you get. So, and this is a set of the two different kinds. So this one's basically what's on there. It's just replacing the parts with metal parts. They usually come with a little drive gear. Now the downside is the ones that are coming on Ender 3s currently, you know, on the shaft of an Ender 3, this is a stepper motor that might be driving one of those. And this little guy is going to go on here. On the current Ender 3s that I've been getting, they're pressed on. So they're like a heat shrink fit. And you cannot get those off of there without heating them up and pulling them off with some kind of gear puller. You're not going to just pull it off. They don't have the little set screws like these. So they don't have this. So if your printer has a pressed on gear here, unless you have another stepper motor, which they're not expensive, but unless you have another stepper motor or a way to get the pressed on drive wheel off of there, you're not going to be able to change any of this because you're stuck with that on there. So before you do any changes on this feeder, make sure you're able to get that gear off of there. Now on this kind, you're probably still okay. The only downside would be if for some reason, if this little roller didn't line up with what you took off of there, which it should be fine. But if you don't think you can get this off of your existing stepper motor, and you don't want to buy another stepper motor just to put in there, then you're kind of limited to this kind, where it's just a metal version of what you already had, which is better because it's not going to crack or do anything like that. But better than this, if you're going to make the upgrade, this kind is better. And this gun is different because it has two little drive wheels that are geared together. So this one would be mounted on the stepper motor. And again, it's going to mount with set screws, which does mean you have to be able to get the pressed on one off of there, or else you can't do this. And then these little teeth here will mesh with the teeth on the handle. And what that does is now both of these are turning. On here, this one is turning, but it's not driven. It's just an idler, right? So it just kind of holds the filament in place. But here, you're gripping the filament from both sides and really have a lot more control over feeding that filament into your hot end. So this is a better type, but you do have to be able to get your old pressed on wheel off of there. Otherwise, you can't get that one on. So that is a thing that you have to be careful for. On these, you do get what you pay for. So there are some really cheap versions of this. And what they typically have as their weakness is, I don't know if you can you, let's see, how close can we zoom in? It's going to get kind of blurry. I think you can tell though. All right, so on the bottom of these gears, there's a little chamfer there, so it's an angle. The really cheap versions of these don't have that angle. You could probably file it in there or whatever, but if it doesn't have that angle, that chamfer on the bottom of these teeth, then it is going to eat away at this metal right here. It's going to eat away from the aluminum. It's just aluminum. And eventually it's going to wear it, kind of like the other ones did, wearing through the hole for the filament. You know, it'll eat it away, and you'll have to replace them. Now, they're not terribly expensive for the better ones even. The better ones are only in the $20 range, or at least they used to be. I haven't bought one in a while. But if you're going to upgrade your feeder, maybe you want better control over your filament path, which is always good, and you think, you know, that's a reasonable upgrade to do, then just make sure that you're able to actually do the upgrade before you go buy the part. And a lot of the Ender 3s currently have pressed on gear or pressed on drive wheels on this stepper motor shaft that, unless you have a gear puller and a way to heat that gear up, you're probably not going to be able to get it off of there. It takes about, I actually did the calculations in the machine design class, and it takes about, I think it was 200 pounds of axial force to pull those things off of there if you don't heat them up. And so just make sure that you have some way to get that thing off of there. Or just buy you another stepper motor and put it on there. These are all what's called Nema 17 stepper motors. They look different sometimes. Like you'll see some that are this wide, and I don't have a good example, but some that are half this size or whatever. And so basically, the longer this thing is, like in this direction, the more torque it's going to be able to apply. And the shorter it is, the less torque. We'll talk about the inside of stepper motors at some other time, but that's general. They're all called Nema 17s on the solid printers that we're using. And the 17 actually refers to the distance between this and this. So it's actually the way it's going to mount to the printer. And I think it's 17, but it's 1.7 inches is that distance to that distance. Okay, so we'll come back tomorrow at the same time again. I did see that, hey, actually one or two people might have clicked in early. That's good. I wasn't even watching the chat. Let's see. I don't see anything over there. Okay. We'll carry on. If you have some questions, put them in Discord. I'll probably not look at any graded stuff until this weekend. So if you're putting things in Moodle for grading, it probably won't get looked at until this weekend. And we'll see you on tomorrow morning.